Okay. Let's make this focus. No, let's make this focus. I hope it's going to focus. Yeah, it seems to focus. Okay, so we're going to start by considering a really basic question in mathematics, which is, what does it mean to count something? Okay, so this is so basic that people didn't ask it for the first several thousand years of mathematics. But what does it mean to count? So now people, so Cantor, this guy, George, I don't know how, I'm going to say George, but I think there's no, it's like Georg or something. He's German. Was German. So he said, okay, what does it mean to count something? It means to put something into a bijection with the positive integers. Let's go with that. I'm not sure if he said exactly that, but let's go with this idea of a bijection. So if I have my class, my rather tiny class of students, so it's in particular a subset of the positive integers, like a prefix of the positive integers. So I have 9 students. I would say, okay, 1, 2, 3, 4, 5, and so on, right? So you establish so you have a first one, you have a second one, you have a third one, and we may not care about the order of these things. It's not like I'm saying the tallest student, the second tallest student. Like, I just want to count the students. I want to say, you, you're 1, you, you're 2, you, you're 3. So whatever, we don't care about the order. Okay. So do we accept that counting means, I get this, so it doesn't, it's a bijection to 1, 2, 3, 4, and then at some point, if I've got an infinite set that I'm counting, then I can go on forever. If I've got a finite set, I can get 1, 2, 3, 4, 5, blah, 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 11, and then I'm done. Okay, so that's a bijection to so bijection means it's 1 to 1 and onto, and in this case, I can only make it onto if it's a finite set I'm counting. I can only make it onto by taking a prefix. If it's an infinite set, then I can make it onto all of the positives. Okay. So do we believe that this is what counting means? One, 2, 3, 4, so on. Okay. Any objections? Okay, so if you believe me so far, that's good, because it took a while for people. So like I said, if you have 3 overhead markers, actually I have more over there, but I have 1, 2, 3. Okay, I have counted them. I have said this is 1, like whatever order they were in. This is 2, this is 3. So there, I've established this bijection to this subset. Okay, so if you can establish this relationship, then we're going to say that the set, if you know, this is the set of overhead markers, it is countable. I can establish this bijection. I can say this is 1, this is 2, this is 3. Okay. If I had an infinite set of these, it would still be countable, because if I could establish such a relationship, I could say this is 1, this is 2, this is 3. So let's consider some infinite sets that are countable. What about the positive even numbers? What is the obvious way to map the positive even numbers to the positive numbers? Well, you divide by 2. So which, you say, okay, 2 is the first one, 4 is the second one, 6 is the third one, 8 is the fourth one, right? So you say, okay, then if you give me I have a way of enumerating these things. If I could write a little program that would list these numbers, and eventually for any positive even number, it's going to hit it. So so the positive even numbers are countable. It's an infinite set, but it's countably infinite. Oh, I didn't start the timer. I may get a grocery delivery at some point during this lecture. I will just sort of answer the phone and tell Perry, the delivery guy, that yes, I will be down after the lecture. Okay, so even numbers are countably infinite. Everybody believes that. I hate not being able to see students. Okay, so what about all of the integers? Okay. Well, what we can do is we can say 0, 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4. Okay, does every so what is my procedure? It is I can say this little program for I equals, okay, so print 0 for I equals 1 to infinity, print I, print minus I, and 4. Does everyone believe that this little program, for any integer you care to think of, eventually this will print it? Okay, what would be the problem if I said, okay, I'm going to first list the positive integers and then list the negative integers? Instead of interleaving them like this, I'd be say, okay, well, print 0 for I equals 1 to infinity, print I, and 4 for I equals 1 to infinity, print negative I, and 4. What's the problem with this program? Yes, this is never going to stop. So if you tell me, okay, well, will this ever print -1? No, it won't, because this is never going to stop either. But for any number you name, it's going to hit it eventually. Here, if you said -1, it's never going to hit -1. So this is not what we want to do. So, but because this program exists, the integers are countably infinite. Okay, the positive integers are countably infinite, and the positive even numbers are countably infinite. The integers are countably infinite. What about rationals? Okay, so any finite set is countably infinite because you choose some order, and then so from now on we're only going to care about infinite sets for the rest of this class. I mean, all that finite stuff, that's too easy. We want hard stuff. We want infinite. So what about now I just showed you that stuff about this program works, this program doesn't work, because you have to think about that for the when you do the rationals. Now the rationals also you have to be a bit careful. Oh wait, there is a question. Yeah, okay. So let's only consider the rationals between 0 and well, actually, let's exclude 0. Yeah, let's exclude 0. It doesn't matter, but let's exclude 0. So we're looking at rationals in 0, and I'm going to include 1. So this notation, if it's an open bracket, I've been using this in the assignments and everything. It's an open bracket means it excludes this endpoint, and it's a closed bracket means it includes it. So I want to show that these are countably infinite. So what I'm going to do is say for, I'm just going to check that code. For now, you're going to see why I say for j equals 1 to, I'm going to do it that way. I'm going to say I. For I equals 1 to infinity. For j equals 1 to I. If do people prefer angle brackets or so this means greatest common denominator. So how would you check this? You check this with Euclid's algorithm. So do people prefer if I write GCD or I can write angle brackets? Print, this is why I was messing around with the order. Print J over I, right? And if, and 4, and 4. Okay, so what's angles? Good. Okay, so what's this going to do? Well, I is 1, j is 1. It's going to print 1. Then I is 2, j is 1. It's going to print, and the greatest common divisor of I and j is 1. So it's going to print 1/2. Then I is 2, j is 2, but now the GCD, the greatest common divisor, is 2. It's not 1. This, okay, this would be a double equals. And so it's not going to print 2 over 2 because 2 over 2 is 1. Okay, so we've already covered that. So now I is 3. It's going to print 1 over 3, 2 over 3. It's not going to print 3 over 3 because GCD of 3 and 3 is not 1. Okay. Then it's going to print 1 over 4. It's not going to print 2 over 4 because 2 over 4 is a half, and the GCD is not 1. So then it's going to print 3 over 4, 4 over 4, no. Then it's going to 1 over 5, 2 over 5, blah, blah, blah. Okay, so if you pick a rational number between 0 and 1, not including 0, then you can tell it to me in some ratio A, B, where A and B are positive numbers, and you can put it in its simplest form where it's A and B have no common divisor. So this is the GCD of A and B is 1. And then I can tell you, this is recording, I can tell you an upper bound on how many steps my program will execute before it prints your number A over B. Now, I would have to work out how many times it skips numbers to actually figure out which rank it's going to assign A over B. And notice that these things are not listed in increasing order. Right? You go from 2/3 and then you drop down to 1/4. There's a reason for doing it that way. Because we have to. But do you believe that this is showing this for any rational number between 0 and 1, you tell me as a ratio, and I can tell you an upper bound on when my program is going to put that. So this means that, and of course, the 0 and 1 is not actually a problem. If I'm a little bit careful, I can actually make it do all of the rationals. That's a bit sneaky, because I don't want to. I have to be careful and do this dovetailing, interleaving thing a bit more carefully, so that it. So what's the problem if I said something like, if I wanted to list them in increasing order, I would be saying, okay, well, for if I wanted to list them in increasing order, then I would want to start with the smallest denominator, but there is no smallest denominator. So you sort of get that problem that you had up here, where you'd be saying, okay. Any questions? No questions? So people believe that the rationals between 0 and 1 are countably infinite. Is anybody still there? Okay, so that's fine. I mean, that's establishing this nice bijection. Now, so where does the problem come? Well, not all sets are countably infinite. Yes. Have you seen this? Okay, so I'm starting with this because when we talk about the halting problem, people keep saying diagonalization. And it's a proof by contradiction. And you keep thinking, like, why is it called a diagonalization? What's diagonal about this? And the reason it's called a diagonalization is you see that if you see Cantor's proof that the reals are uncountably infinite. Okay, and so some of this is not a surprise. So now, so the rationals in this interval are countably infinite. Now we're going to say, so the rationals are countably infinite, but the reals are not countably infinite. They're uncountably infinite. So this is the kind of thing where if you go home and somebody says, what did you learn in school today? And you say, oh, I learned that some infinities are countable and some infinities are not countable. And they're going to think, like, what do you mean an infinity is countable and not countable? So the reals in 0 to 1 are uncountably infinite. So this is a proof by contradiction. And so I think in some message, in some announcement, I referred to this as mathy judo, because it's sort of a proof by contradiction is sort of you assume something and then you use that assumption to reach a contradiction. So here it's like we assume somebody can do something that we think is impossible, and then we use that. Like in judo, you use your opponent's strength against them. Well, here we're going to say, okay, assume that you can do this, then I can use that there is an algorithm for doing this. I can build on your algorithm, use your algorithm as a subroutine to build an example that your thing can't work on. Okay. So, what did Cantor do? He said, okay, so assume there is an ordering of the real numbers. So the real numbers, you can express a real number in this interval. No, actually now I want this to be slightly the other way. I want to include 0 and I want to exclude 1. Okay. It doesn't really change anything, but I'm just, so So now that we're not including one, any real here can be expressed as 0.7215394, blah, blah, blah. Okay. And let's put some other 3/8, 9, 1, 4, 6, 9. Do these line up? Actually, more or less. Let's put the 9 over here. And 0.9849844, blah, blah, blah. Okay, so you can write any real as a 0 point and then some string of numbers. Maybe the real numbers are the friends you made along the way. This sounds like a quote. Okay, that's that rings a bell, but if I stop and think about it, I'll lose track. Okay, and we still have quite a bit to get through today. So now notice that there's one thing about this, which is I'm not allowed to have 0.999. Actually, I'm not allowed to have something like even 31291299999. I'm not allowed to have an infinite string of nines. That's the only thing I'm going to have to be careful about. Okay, I can have an infinite string of eights, but if I have some number and then an infinite string of nines, then this is actually 0.313000. And that's just because this and this are the same thing. And we don't write it this way, we write it this way. Okay. So that I have to be a little bit careful. So Cantor said, let's just write some more numbers, 21774. 5, 3, 2, and 0.15888. Okay, let's just write some numbers. So Cantor said, assume there were a bijection. So these kind of proofs of contradiction is where, so usually in mathematics we use the present indicative, right? You say, assume there is. So this, people didn't always do this. And I realized it one time I was in Italy and I thought, oh, well, look, there's Hardy's Mathematician's Apology in Italian. I thought, but it's a really small book. And I thought, I've read this, it's about mathematics. And I've read this in English, so I should be able to read this in Italian, until I got to the proof that the root of 2 is irrational. And the thing is, then it didn't click when I read it in English, but everything is in the subjunctive and the conditional. So assume it were rational, then there would be a ratio A over B. Blah. And so that was actually beyond the level of Italian I could do. So assume there were. So suppose there were a bijection between the reals in this interval and the positive interval. So you could list. There would be a first one. There would be a first real, a second real, a third real, and you could write them out like this. So maybe this is the first real in this interval. So you could list them. You could. I would have a little program that would generate these numbers, and so Cantor, if you had that, so if you had an order, if you had 1, 2, 3, if you count these, then what you could do, I want this number to be yeah. No, actually, this is fine. Okay. Then you could construct a number that isn't in this list anywhere, right? So this list is going to go on for infinity. But the idea is for any real number you pick in this interval, at some point it appears in this list. It has to, it can't just not be there. Because that's like with my little program for the rationals, for any number you pick, I can tell you that yes, it's in there. And in fact, I could work out that it has to be by this step. You tell me A and B, I can tell you based on A and B. I can tell you how long, an upper bound on how long we take to get there. So here, the idea is you could tell me any real in this interval, and I could tell you that yes, it has to be in this list. So Cantor's idea is you take the first digit here. So we're going to build this number that's not in the list. And it's going to be, so this list is infinitely long. I'm going to take the first digit of the first number in the list, in this list. And the first digit of this is not this digit. It is something other than this digit. So it could be a 5. Right? And now I take this 8 and this digit of the second digit, so I take the second digit of the second number, and then the second digit of this number I'm building is a 4. It's just something that's not an 8. Now I have to be a little bit careful because I don't want to build something like 0.599999999 because like I said. So you just have to be careful not to ever hit a run of, like if you get a 6, you don't turn it into 9. And then you get a 4, you don't turn it. So every so often, turn it into something that's not a 9, just so you don't get an answer. That's the only thing you have to be careful about. This is a 4. So this is not a 4, it's a 7. This is a 7, so this can be a 6. This is 1, 2, 3, 4, 5. This is an 8. So this can be a 9. I just can't have an infinite string of 9s. Okay, so that's how I build my number. Now, what property does this number have? It differs on the first digit from the first number. It differs from the second digit on the second number. It differs from the third digit. In the third digit, its third digit differs from the third digit of the third number, right? So if this number were in here somewhere, we're in the list, it was ith in the list, it was 102nd in the list. Well, it can't be because it would differ from the 102nd on the 102nd digit. So for any number in this list, this is not equal to that because it differs. It differs from the ith number on the ith digit. So I've just constructed a number. This list, infinite though it may be, this infinite list is supposed to contain all of these reals, but I've just built one that isn't in it. And notice this is where you get this diagonal. Okay, because this line is going diagonally. Okay. So it's Matthew Judo. It's a proof by contradiction. We assume that there exists this bijection between the reals in this interval and the positive integers, and then based on that assumption, we could construct a number that we missed. Okay, so that's the proof that the reals in this interval are not countably infinite. They're uncountably infinite. Now you can go a lot deeper into this and get into like, is there an infinity between the countable infinity and the infinity of the reals? And I think then you get into like the continuum hypothesis, blah, blah, blah. We don't need that for this course, Okay, we actually don't need this, except it's a nice way to sort of get our heads around diagonalization and understand why it's called a diagonalization. And uh-oh. Timer start, reset, start. Okay. So people understand countable and uncountable infinities. So let's talk about the halting problem. So one way of sort of talking about limits of computation is to say there are uncountably many functions. There have to be that reals are not countably infinite. I think so. They're definitely infinite. So if they were finite, they would. Okay, now I'm not sure. Like if there's a definition of uncountably infinite that's more complicated than just not countable, infinite and not countably infinite. Proves that reals are not countably infinite. Yes. Okay. So there are more infinities. You get into this Aleph stuff. I think so. From what I remember, the continuum hypothesis is asking if there's an infinity between infinity of the countable infinity and the infinity of the reals, and it's independent of like Zermelo-Frankel set theory and blah blah blah. I don't know. I think it's just if they're not countably infinite. If they're infinite, not countably infinite, they're uncountably infinite. Not sure. I would have to, don't quote me on that. I did also, I posted an announcement that I made a mistake in the stuff about fine-grained reductions. I was saying the strong exponential time hypothesis was the 3-sat or something like that. It's not 3-sat. We have algorithms for 3-sat that run in better than 2 to the n time, in 2 to the n minus some constant epsilon. Those exist. It's actually for ksat. So for some, there exists some k where you can't do that. So I got it right. So, but going pushing on the so functions are uncountably infinite, and Turing machines are countable. So we that already sort of establishes they're uncomputable functions, but that's not a constructive proof. So can we find something that cannot be computed? And we're going to do this with a diagonalization with mathy judo with proof by contradiction. So assume that, so the halting problem says, does a Turing machine, so this is why Turing invented Turing machines, so that he had a model of computation that people would accept, and then if you could show that this couldn't do something. I think everyone is going to accept C as a model of computation. Like if you can do it in C, then it's computable. If you can't do it in C, then it definitely looks, we're going to take that as, we're going to agree that C is, if you can't do it in C, then it's not possible. And C is Turing complete, so actually this is sort of the same, but it's just because C is more familiar, at least to me. So I'm going to use the blue marker because the black marker is, even the good black marker is starting to run out. How would you do this? So you want the halting problem says you're given the C halting problem says given some program written in C, does it stop? It doesn't. Let's forget. Yes. Okay. So that's the trick. But for people who haven't seen it, so you want a program that now it can handle input or not, but let's, oh yeah, you have to so you have to make it take an input. So given a C program, P, and an input X, does P halt on X? Okay. So this is, I mean, you can write a program that says, okay, read the input. If the input is 5, drop it into an infinite loop. So this would actually be quite nice for compilers to be able to do this. So you can get rid of the input if you want, but I think we want the input. So the idea is, could you do this? Could you write a program like this? And the answer is no. Why? Well, if you could write a program like this, so suppose P, given a program P, suppose there exists a program that solves this. So suppose there exists a program H that solves the halting problem. Solves the halting problem. Okay. Then we can write a program H prime that, so I'm going to do this in a couple of steps. Halts that given P and X, comma, halts if P on X halts, and otherwise drops. Now, I'm going to change this like into an infinite loop. Okay, we could do this, right? We would write, so void H prime given so char, so given a string P, given a string X, so if H Px, so if P on X halts, return, else for I, well, for forever, do this stuff, loop, just loop, do nothing, and if. Right, so this is here, here. Okay, that's easy. I've just written H prime. Wait, oh, there's stuff going on. Oh no, nothing has changed much. Okay, so that's fine. So if P on X, if P on X halts, then this halts. If P on X doesn't halt, then this doesn't halt. Okay, but now we're going to do the tricky thing. So halts if P on X. So this is if H says P of X halts, and otherwise it. So now we're going to put in here what happens if it doesn't halt and otherwise drops into an infinite loop. So now if H says P of X, okay, I just have to get this right. If not HP of X, then it halts. And otherwise it doesn't. Right? So okay, so now we have a program which we're going to call H double prime, that if it's given a program and it's a program and an input, if the program halts on the input, then H double prime doesn't halt. And if the program doesn't halt on the input, then H prime halts. So this is like, it's a bit like I am lying, okay? So now we're just going to change it again, where this is going to take only one argument, and it's going to take only one program. It's going to take the argument is the program, and if the program halts on itself, then this, if the program doesn't halt on itself, then this will halt. And if the program does halt on itself, then this will not halt. A program is a string, right? Remember I had char pointer, char pointer. So now you have a program which, given any other program, says, okay, if program P given itself, and it makes sense to give programs themselves. For example, have people taken compilers? One of the ways that you test a compiler, when you first write a compiler, you can't compile it with itself. So you do this manually. You compile it manually. This is how they did the C compiler, for example. You figure out how the C compiler would compile itself. You do that manually. And then to test whether your compiler is working, you compile it with itself and see if you get the same code back. So for example, compilers are programs that can be run on themselves. So look, here is the code where if there exists a program that says H that solves the halting problem, then I can write this. I can have a program that takes a string, asks if that string as a program halts on itself. If it doesn't, this will halt. This is actually okay. So H, this would be H double prime, H triple prime. If it doesn't halt on itself, then this halts. And if it does, then this doesn't halt. Okay. Then what does H prime do on H prime? H double prime do on H double prime. So it's gonna take a description of itself, which is just here, right? Because we can include H, this H as a subroutine. Right? So down here we have this H as a subroutine. So it takes this whole description, which is a string, and it's given this as a string, as an argument, and it calls H. And then if H says that it will halt, then it doesn't. And if H says it doesn't halt, then it does. So we've reached a contradiction. So the halting problem is not computable. There is no algorithm that does this, that tells you, given a C program P and an input X, does P halt on X? Are people happy with that? Like, could you, if I told you there existed this program, could you build this H double prime? Maybe H double prime was a bad example. It was a bad name. Okay, so write a program Q. Given P and X, halts if so now we've got halts if now we're given P halts if P doesn't halt and drops into an infinite loop. So this is not a hard program to write, right? Like it's right here. It's a small voice. Okay, so that's the halting problem. So that's, I mean, even though we're showing that something is harder than like NP complete, this one was actually done in the 30s. It's like, okay, there are limits to computation. So this is a fairly easy thing to see. So let's, so that's the first diagonalization. The second diagonalization that we're going to see is Kolmogorov complexity. Has anybody heard of Kolmogorov complexity? Sorry, I get that wrong. So what does this prove? It proves, so since we get a contradiction here, so what does Q do on Q? If it halts, then H is wrong, because H says Q on Q. If H says Q on Q halts, then Q on Q doesn't halt. And if H says Q on Q doesn't halt, then Q on Q does halt. So we've reached a contradiction. So that means that there doesn't exist a program H that solves this halting problem. So it's not actually, like I said, it's like this, you're building something, you're assuming it's a diagonalization because you're assuming H exists, and then you're using it as a subroutine to build, to fool it, to reach the contradiction. Oh, this is this is like, so it's for colon, this is like, it's the same effect as while true. This will just never stop. So if you do for semicolon semicolon, it's saying, well, don't do anything to initialize it, don't do anything as your test, and don't do anything, don't increment I or something like that. It will just, that for loop will just do nothing forever. Okay, so it's an infinite loop. Okay, so and then you can do a lot of, yay, reductions by, for example, it's not possible to tell if a certain line, in general, it's not possible to tell if a program will ever execute a certain line. And you can show that it's not possible. You're given the code for the program and somebody says, are there any conditions in which it will reach this? Well, you can reduce the halting problem to that. What? How? Well, you just say, okay, well, I take a program and I want to tell if it halts anywhere where it would say halt, I'm going to redirect it to say, okay, go to that line. So it halts if it executes that line, and then you put something in where you say, okay, I'm only going to reach this line if it halts. And so now you can give it to your compiler says, oh, I can tell if a line is executed, and you give it and you say, okay, is this line ever executed? And that's the only line that says halt. It's equivalent to saying, does this program halt? So there are lots of things in compilers where it turns out that compilers cannot do something because it would mean if they could do that, then you could solve the halting problem. So I think there's but like from 20 years ago, I think it's called Rice's theorem. So the Kolmogorov complexity is also something we would like to do, and it's also incomputable. So let's do Kolmogorov complexity, and then this is the end of the course. Well, there'll be a review. But so this is not bad, I think. This isn't exactly C. I would have to have curly braces here. It's like C. It's basically C. Okay, so Kolmogorov complexity. The Kolmogorov complexity of a string is the length of the smallest program that outputs that string. Okay, so Kolmogorov. Length. So let's say it's the length in bytes. The shortest C program that outputs X and stops. Okay, so I like C, so this is going to be a C program. Notice that one of the nice things about Kolmogorov complexity is, if you think about it, the Kolmogorov complexity doesn't really matter. Not much changes if you switch programming languages. Why? Because, for example, if you say, oh, I don't like C, I like Java. And you say, okay, but Travis is talking about the complexity of this thing in C. And you want to write in Java. Then what you could do is just write a Java compiler in C. Oops, this is not recording the top of the screen. That's recording enough. Okay. So if you want to, for example, if I insist that some programming assignment must be written in C, and you don't want to use C, you want to use Java. So I am not recommending that you do this. This would probably annoy the marker. It says programming assignment must be done in C. You want to do it in Java. So let's say you write program P in Java. Now you want a program that does the same thing as P, but in C. Well, and you want a C program equivalent to P. Let Q be a Java compiler written in C. Then QP, so QP is going to be a C program, right? Like if you write Q and you write you pass P to Q as an argument, so you embed Q in the program and pass it to the subroutine. You embed P in the program and you pass subroutine Q is a C program that does P. How much longer is this than P itself? Well, it's only a constant because you say, okay, I write Q. Well, Q doesn't depend on P. So Q is a constant length. It just depends on your choice of programming languages. So the complexity, the length of the program doesn't switching between programming languages as long as you can write a compiler for one in the other. Changing programming languages doesn't actually change the Kolmogorov complexity by more than a constant. Okay, so I'm going to say C here, and this is why my choice of programming language, as long as it's Turing complete, it doesn't really affect anything. So Kolmogorov complexity, you can define everything in terms of Turing machines. That's just really another program. Okay. don't please do this. Like if you want to write your program in some weird, like if you want to write a programming assignment in some weird language, do not do this. Do not turn in your program in the weird language preceded by a compiler for your weird language written in one of the languages the marker knows. I don't think that would probably not convince her to give you lots of marks. Okay. There is a reason why you would want to know the length of the shortest program. And the reason is sort of statistics and inductive learning and stuff like that. So if you've heard of this thing, Occam's razor. So hypotheses are, oh, I forgot to start the timer. So if you want to sort of evaluate, if you want to build a model, if you choose a string and it's random, it's not going to be compressible. So if you have a hypothesis according to which some string is highly compressed, which compresses something, it's like this: the smallest explanation, the simplest explanation is probably true. That can actually be formalized in terms of Kolmogorov complexity. So if you choose a string at random, it's unlikely to be highly compressible. So the better compression your model gives, you've actually gotten more evidence for that model, because if it were some other model, the chances of it being more highly compressible is small. So that's why people, you get into like, if I choose a random string of bits, the chances of it being compressible. So for example, if you see a string of bits, and it's 0, 1, 0, 1, 0, 1, 0, 1, then you're going to think, okay, this is probably, and you look at it and say, it's what is this string doing? Well, it's 0, 1, and then it's repeating. And I say, no, the string is randomly chosen. And you say, oh, the chances of that happening, because I've just seen a pattern in it that allows it to be highly compressed. And the chances of me being able to find a pattern that really compress a random string are very small. So that's why if you find a pattern and it allows you to do good compression, then you count that as evidence for the pattern. Even though, for example, if the string 0, 1, 0, 1, 0, 1 is just as likely to be randomly chosen as any other string, but we take it as evidence that there's something that we've figured out the model because it allows good compression. Okay. So if we could do Kolmogorov complexity, we could do data compression, and we could do this really, really good machine learning. So this, what I just said, is basically known in machine learning as the minimum description length principle, more or less. But we can't do this. So also we can try to approximate it, but even that's hard. I think I'll put that on the next assignment, the difficulty of approximation. So there are reasons why, if you're given a string, you would like to know the length of the shortest program that outputs that. So this would be the ultimate compressor, because if you had something like Lempel-Ziv, and Lempel-Ziv works really well, this could always just be a Lempel-Ziv compressor that's going to take a constant term and then the description in Lempel. So this sort of dominates all other compressors. Why can we not actually achieve this thing? By a diagonalization. So assume there is a C program K that computes Kolmogorov complexity. Kolmogorov. So assume that there is a program. Does anybody see sort of how this is going to go? Of my 8 remaining students. Okay. Assume there is a C program that computes the Kolmogorov. Yes, it's similar to the halting problem. Very similar. It's a diagonalization. Well, notice, so K is a program. So actually, K is usually what we write to indicate the Kolmogorov complexity. So let's call this something. Let's call this P. So there's a C program P that computes the Kolmogorov complexity. That is P X. It outputs KCX. Okay, but P is a program. So what I can do, notice that for any fixed Kolmogorov complexity, not all strings. If I consider strings in increasing length, there has to be one that's eventually I'm going to find one. Actually, there are going to be an infinite number which have Kolmogorov complexity larger than that. So let's say, what is the length? The length of P. Add some slack. So now let's write a program Q. So this is so Q is going to take okay, I'm going to build this from yesterday. So for X equals, so for N equal 1 to infinity. For X in, so this notation is, sorry, not sigma star. So this I'm saying I'm considering strings. So this is the alphabet sigma. Sigma to the n is the strings of length n. And so I'm going to consider all of the strings of a certain length. So what is the length of P? Let's say length L. If P on X is greater than L plus a million, print X. Return. Yeah, I don't need semicolon. End if. Okay, so program Q is going to be void Q. Doesn't take an argument. I'm actually never going to get here. But okay, so what is this going to do? We assume that there is a program that computes the Kolmogorov complex. So down here, as a subroutine, we have this program Q. So now Q is going to go through, and it's just going to loop through the strings, and it's going to ask for each string, does P say that this is a complex string, where complex means much, it requires a program much longer than P itself. So let's say it has length L. So remember that L here, we could actually substitute P of P. And then we're giving ourselves some slack. What is this million characters for? This million characters is this slack is to take in this part of Q. It's much less than a million characters. Right? It is. So what is this program going to output? It's going to output the first string it encounters that P says is complex. Complex meaning more complex than the length of P plus a million. But this is a program, and then it's going to stop. But this is a program that outputs exactly that string. And the length of this program is L plus, like at most, a couple of hundred. So if P is right, then the string that this thing outputs is really complex. But we've just written a program for it that is not complex. So P says that whatever this outputs, now the trick is, of course, that P cannot say that everything is simple. Because if P said everything is simple, then this L is a constant, then it would be saying that for any string I choose, I can write a program that will output that string that has length less than L plus a million. And by counting arguments, that can't be true. So if P is accurate, it has to say some strings are complex. But if it says the first string that it says is complex, it's not complex. Have you, if anybody's heard, so we're about out of time, have you heard of that argument that there are no boring numbers? If there's, so imagine that, okay, so the argument is there are no boring numbers. Imagine that there are boring numbers. Then there is a smallest boring number. That is an interesting property for a number to be the smallest boring number. Therefore, it's not a boring number. So this is the same way. It's like, okay, there, if you say, okay, the smallest complex number, no, complex is, no, I don't mean complex like in the complex way. I mean the smallest number that has a large Kolmogorov complexity, much bigger than P itself. it has, because we can construct this program Q, it's not hard to write. So the first string that has a large Kolmogorov complexity has a small Kolmogorov complexity. So we get a contradiction, and so the Kolmogorov complexity is any questions about this stuff? So if we assume that there's this program P that tells you what is the length of the smallest C program, there's a C program P that tells you what is the length of the smallest C program that outputs a given string, then we can use it to build a program that will output a string that P says doesn't have a short program. And this program will be shorter than P thinks it is. So the Kolmogorov complexity is incomputable. Okay. This, if I were writing lecture notes still, this would probably be better in the lecture notes than it is like this. It's hard to do this in Zoom. I'm gonna, like, does everyone see why this is true? Or, okay. I can't see anybody's faces. I'm way behind on something, so I'm actually, there aren't going to be lecture notes. But it's the same. It's the same as with the halting problem. If there were a program P that solved the halting problem, then we could turn its strength against it and build a program that would, and it would, in both cases, it calls P as a subroutine. So if P says it's going to behave this way, then it behaves some other way. In this case, if P, you just have to run through and find a string that P says doesn't have a small program, and then you say, okay, I print that. Bit of a rough lecture to end but you see, this is sort of fun stuff. And it's not that hard, and it's kind of deep. Oh, and just to end it with, okay, so we're right on time. Kolmogorov, so like I said, he was a famous statistician. Just to link back for closure, to link back to the beginning of the course. Do you remember Karatsuba's algorithm? So remember I said Karatsuba, he was in a seminar and somebody conjectured that multiplication took, there was a lower bound for multiplication that was quadratic. That you couldn't do better than that, and Karatsuba went away and came back with this algorithm that beat quadratic, and the person who gave the lecture was so impressed that they submitted it to a journal and got it published with Karatsuba's name on it. That was Kolmogorov. So also, I think somebody else who's been mentioned in this course, if you go back, their high school was actually the Kolmogorov High School. It's a small world. So that's it. Monday will be review, and Wednesday will be filler. Maybe I'll talk about research, sort of how you can, what you can do with algorithms in research stuff. But we're out of time, so thank you for showing up. Okay, I'm going to stop the recording. Best 5 out of 8. Final exam is on August 5th. Any practice question? Yeah, I'm going to post the exams from last year. The exams from the 2 previous years. Cheers.